A commercial water-cooled chiller removes hundreds of tons of heat from a building every hour. But thermodynamics dictates this thermal energy cannot simply vanish. Instead, the chiller absorbs this massive load, transferring it directly into a closed condenser water loop. This leaves a critical problem. To reset the refrigeration cycle, the chiller must find a place to dump this concentrated heat. The solution is a cooling tower, a dedicated heat rejection system acting as the thermodynamic bridge between the closed mechanical plant and the open atmosphere. Pumps push the hot condenser water out of the basement mechanical room and pipe it up to these structures, typically located on the roof. Up here, these massive structures take over the process. To understand how they work, we have to look past the spinning fans and engineer a cooling tower from first principles, analyzing its internal components, flow architectures, and the strict mathematical boundaries that govern its performance. Because no matter how advanced a chiller is, it is mathematically useless without a cooling tower. It is the final, non-negotiable gateway for heat to leave the system. The core thermodynamic equation governing a cooling tower is straightforward. Evaporation plus air contact equals heat rejection. While contact with cooler air provides sensible heat loss, the primary mechanism is latent heat transfer. As water evaporates, it extracts physical energy directly from the remaining liquid, driving its temperature down. Evaporating a single drop is easy. The engineering problem is executing this process on thousands of gallons per minute. To scale this up, hot condenser water is forced through spray nozzles, atomizing the fluid to instantly multiply its surface area. But atomized mist falls too quickly. It needs to pass through a dense honeycomb structure known as the fill. This fill acts as the primary heat and mass transfer engine. It forces falling water to spread into a microscopic, slow-moving film, maximizing surface area and contact time with the air. To maintain the evaporation rate, the system requires continuous forced airflow. A massive mechanical fan at the top of the structure constantly draws fresh air upward, directly through the falling water film. Because the fan pulls rather than pushes the air through the unit, this specific configuration is known as an induced draft tower. It is the absolute standard across commercial HVAC plants. This induced upward draft creates a mechanical loss. High-velocity air will physically strip small droplets from the spray and carry them out into the atmosphere, wasting treated water. To prevent this, engineers install a mechanical baffle called a drift eliminator. Escaping droplets strike this corrugated layer, condense, and fall back into the system. Gravity pulls the successfully cooled water down into a large collection basin at the base of the tower. From here, return piping routes the cold condenser water back down to the chiller, completing the thermal bridge. Every internal mechanic of a cooling tower serves one singular purpose, acting as a massive surface area maximization machine, evaporating water as efficiently as possible. When thermal loads reach massive industrial scales, the physical architectures change entirely. In large power plants, engineers use natural draft towers. The hyperbolic shape of the concrete creates such a powerful updraft that mechanical fans aren't required. Returning to commercial mechanical draft units, engineers must select between two primary internal airflow architectures. In a counterflow configuration, water falls strictly down, while air is pulled strictly up. Moving the fluids in exact opposition maximizes the thermal gradient and creates a highly compact footprint. In a crossflow tower, water still falls vertically, but the air is pulled horizontally across it. This geometry generally simplifies access for routine maintenance. Beyond airflow, engineers must also consider the working fluid itself. Using the atmosphere for cooling inherently introduces the risk of contamination into the condenser loop. Most commercial buildings use an open-circuit system. The hot condenser water is sprayed directly over the fill, exposing the primary loop straight to the outside air. However, if the process fluid must remain pristine, a closed-circuit system is used. The fluid stays isolated inside a sealed serpentine coil, while a secondary, completely separate water loop sprays over the outside to cool it. Selecting a tower configuration is a strict engineering trade-off that balances thermal efficiency, footprint limitations, and maintenance accessibility. To evaluate a cooling tower's actual performance, we rely on exact mathematical metrics to measure the work being done. This chart shows the temperature deltas inside the system. The first variable is the hot condenser water arriving from the chiller. Let's say this enters the tower at 35 degrees Celsius. The second variable is the cold water leaving the basin at 30 degrees Celsius. The absolute difference between these two numbers is the range. In this instance, we have a range of 5 degrees. Range simply represents the thermal load dictated by the chiller. It shows exactly what the tower did, but it reveals nothing about how efficiently the tower is capable of operating. To determine efficiency, we have to look outward and measure the environmental constraint. Standard dry bulb air temperature is mechanically irrelevant here because it does not account for atmospheric humidity. Instead, we use the wet bulb temperature, which represents the air's absolute evaporation potential. Let's plot our ambient wet bulb at 27 degrees. The delta between the cold water leaving the tower and this ambient wet bulb temperature is called the approach. Here, we have an approach of 3 degrees. This reveals an unbreakable law of thermodynamics. A cooling tower can never cool water below the ambient wet bulb temperature. You could double the size of the fan, and that limit remains absolute. While a smaller approach signifies a highly optimized, efficient tower, the entire central plant's efficiency is ultimately capped by the local climate's humidity. This continuous evaporation process introduces a severe, ongoing mass balance problem for plant operators. When water evaporates, it leaves as pure vapor. This strands all its dissolved minerals, salts, and suspended solids behind in the basin. If left unchecked, these concentrated minerals trigger catastrophic scaling. Calcium and magnesium crystallize, rapidly encrusting the internal surfaces of the system. This mineral scale acts as a stubborn insulator, destroying the heat transfer efficiency of the fill media and eventually choking the chiller's condenser tubes. The automated mechanical solution is the blowdown system. When sensors detect high dissolved solids, a valve opens, discharging the heavily mineralized wire. Makeup water is then introduced to replace what was lost, safely diluting the basin. Alongside blowdown, the water requires rigorous chemical treatment. Without precise biocides and corrosion inhibitors, the hot, oxygen-rich environment becomes an ideal breeding ground for microbiological growth and rapid metal degradation. Keeping the equipment alive requires operators to maintain variable speed fan optimization, immaculate fill conditions, and strict dissolved solids monitoring. A massive chiller plant operates as a single interconnected organism. The chiller, the condenser pumps, and the water chemistry all rely entirely on the precision and health of the cooling tower to function.